This unit focuses on solid, liquid, and gas. Now, as the three phases are changing from one phase to the next, there is a breaking or formation of intermolecular forces. Intermolecular forces, they are the attraction between the molecules. So the attraction between this water molecule and this water molecule, that attraction shown in dashed line is called the intermolecular forces. There are three different types of intermolecular forces that will show up within the next 2 to 3 videos. One is hydrogen bonding, and the next is dipole-dipole, and lastly is the London dispersion forces. We'll most likely focus a lot on the transition between the liquid and the solid. Why not the gas? Well, the gas will have intermolecular force between the molecules sometimes, but sometimes they are apart. The amount of intermolecular forces in the gas is very minimal, so therefore they are able to behave as gas because they're not bounded together by this intermolecular force, and they're just like flying around. Whereas the liquid, they're close enough to each other, there's enough interaction where there's an intermolecular force, whether it's hydrogen bonding, dipole-dipole, or London dispersion forces, that comes to play. And of course, solid, they're really tightly packed together, so therefore the intermolecular forces do highly apply here. So what is this video really going to focus on? We're going to focus a lot on hydrogen bonding, and the next 2 videos will be on dipole-dipole, then London dispersion forces. Now, before I go into hydrogen bonding, do you remember how to draw Lewis structure for H2O and NH3? If you're able to do so, go ahead and pause this video and draw the Lewis structure for water. In fact, draw 2, one here and another one here, and 2 NH3, and come back. Now, if you're unable to draw them, you can draw them after you have seen the key. And here are the molecular Lewis structures for both of these guys. Now, water, let's talk about water first. There is an attraction between the hydrogen of here and the oxygen of the other molecule. And I'll note it in red with a dashed or dotted line like this. So this dotted line, this is the intermolecular forces that I was talking about, and this one is hydrogen bonding. And this also exists in ammonia, right here, between this H and the other nitrogen of the other molecule. And this is also called hydrogen bonding. So what is this hydrogen bonding? Hydrogen bonding is the attraction between the hydrogen of one molecule and either fluorine, oxygen, or nitrogen of the other molecule. Now, why is there even an attraction? Why not between a hydrogen and this hydrogen? Why is there an attraction? Well, this has to do with the electronegativity. Oxygen has very high electronegativity, so they like to draw in a lot of electron towards themselves, and in fact not just their own but also from the hydrogen as well. That causes the oxygen to have a partially, not full, but partial negative charge due to having a large electronegativity value. Same for nitrogen. Nitrogen has a lot of electronegativity value in comparison to the hydrogen, so they're partially negative. Now you see the squiggly line and a minus. That squiggly line is a delta sign, and the minus shows that it's a charge of negative. Well, the hydrogen, because there's some lot of their electrons are going towards the oxygen, the hydrogens are exposing their proton, and proton has a lot of positive charge on it, so therefore they're going to be partially positive. So all of the hydrogens here are partially positive, and even an ammonia as well. And we learned in chemistry that opposites attract, the negative and the positive. So therefore, that partially positive hydrogen and the partially negative oxygen from the other molecule are going to interact with each other, and that interaction is called hydrogen bonding. Now, it only applies for fluorine, oxygen, and nitrogen, and not for any other molecule. And this is because F, O, or N, or I like to call it fun. It's not FUN, but fun, has strong electronegativity. They're one of the highest electronegativity. So they have this special name called hydrogen bonding. Out of the three intermolecular forces, hydrogen bonding, dipole, and London dispersion, this one is the strongest. So what do I mean by out of the three? I have mentioned before that there are three types of intermolecular forces, and hydrogen bonding is going to be the strongest. So I put strength of intermolecular force strong. It doesn't mean that it's stronger than like a covalent and a ionic bond. They're much stronger, but they are hydrogen bonding is the strongest out of the three that we have discussed before. Well, how does this relate to phase changes going from solid to liquid and gas? Well, the thing is, as they're making that transition from solid to liquid to gas, the hydrogen bond, the intermolecular force break. Now, going from solid to liquid, this is when it starts melting, right? From going solid to liquid, think of ice melting into water, liquid, and there is a breakage of some of the hydrogen bond because there's a lot of flexibility and movement of the water. That time, or that point in which the temperature is set to melt, that we call that a melting point, where it changes from solid to liquid. And why does it change from solid to liquid? Is because that heat is being utilized to cut this hydrogen bonding. Then going from liquid to gas, this is the boiling point, meaning the temperature in which it goes from liquid to gas. And what that happens is that heat is being utilized to cut all of the intermolecular forces within the liquid molecule. And so they are able to form gas, and they're free from each other, and there is a very little or no intermolecular force within the gas. Now let's do a learning check. Which of the following can participate in hydrogen bonding? So try to see where you can even put the partial charges, and see you come back and check this video, and we'll go over it together. And here is the key. The ones in the boxes are the ones that are participating in hydrogen bonding. So why not the others? So let's talk about a little easier one. This is HNCl and HCl. It doesn't participate in hydrogen bonding. Even though chlorine might have a higher electronegativity and it will have a partially negative charge, this is because hydrogen bonding only refers to some molecule that has a fluorine, oxygen, and nitrogen. And this chlorine is none of that. So therefore, it doesn't participate in hydrogen bonding. In fact, this one participates in another intermolecular force called the dipole. How about over here? Now, you may say, well, it has hydrogen, it has oxygen, so why not hydrogen bonding? The thing is, the hydrogen must be directly attached to the fluorine, oxygen, and nitrogen, but it's not. The hydrogen is attached to carbon, and it's not directly attached to the F or N. Over here, you see that the hydrogen is directly attached to F, O, or N, so therefore it works. But not this one, because this will it's not directly attached. The hydrogen not directly attached to the oxygen. It's from carbon then to the oxygen, right? There is another step. So therefore it wouldn't work.